Hey there, science fans! Ever wondered what makes batteries work their magic? Or why a shiny apple turns brown after you take a bite? Or how amazing green plants manage to make their own food from sunlight? The answer to all these questions and so many more involves some super cool chemistry. It's all about a special kind of reaction called redox reactions. Now, redox might sound like a really complicated scientific term, but don't you worry your curious minds about that. We're going to break it all down, make it wonderfully simple, and discover how these fascinating reactions are happening constantly all around us, every single day, in every single way. They are truly fundamental to understanding so much of the world we live in and interact with. Redox reactions are kind of like tiny, invisible tug-of-wars that are happening all the time with even tinier particles called electrons. You can imagine electrons as little packets of energy zipping around. Some atoms, which are the basic building blocks of everything, absolutely love to give these electron energy packets away. On the other hand, there are other atoms that are super eager to grab them and hold on tight. This constant give and take, this sharing and swapping of electrons, is precisely what a redox reaction is all about. It's a fundamental process in the world of chemistry, influencing everything from the energy that powers our gadgets to the very air we breathe. Understanding this vital exchange is the key to unlocking many chemical mysteries you might encounter. Now you might be thinking, why should I care about these redox things? Well, let me tell you, redox reactions are the incredible power source behind so many everyday phenomena and essential life processes. They are what make our phone screens light up, they help our bodies digest the food we eat to give us energy, and they even play a critical role in keeping our entire planet alive through amazing natural cycles like photosynthesis in plants. Seriously, without redox reactions, life as we know it simply wouldn't be possible. It's not just some obscure topic confined to chemistry labs and textbooks, it's happening inside your body, right this very second. So, buckle up your seatbelts because we're about to embark on an electrifying and enlightening journey into the amazing world of redox chemistry. In this exciting exploration, we'll take a closer look at what the term redox actually means, breaking it into its two important parts. We'll investigate who's losing electrons and who's gaining electrons in this fascinating chemical game. We'll uncover lots of everyday examples, from how shiny metal can turn into crumbly rust, to how green leaves work their magic to produce sugar using sunlight. By the time we're through, you'll be able to spot these important reactions happening around you and truly appreciate their amazing power and significance in the world. Get ready to have your mind powered up by the incredible science of redox reactions. It's going to be an enlightening and fun experience, I promise you that. So let's get started on this adventure. Alright, science explorers, let's dive right into the very first part of our redox puzzle. This part is called oxidation. Now, the name itself might make you immediately think of oxygen. And it's true that oxygen is very often involved in oxidation processes. That's where the name originally came from. But oxygen isn't the whole story, not by a long shot. The really key idea, the most important thing to remember about oxidation, is that it's all about losing something very specific and very important: electrons. Imagine an atom or a molecule as a little character in a play, and this character is holding some tiny energetic balls, which represent its electrons. When that character loses one or more of those electron balls, we say it has been oxidized. It's a fundamental chemical change. We have a super handy and easy to remember way to keep this straight in our minds. It's a little phrase that chemists love: oil. Now, this doesn't mean the stuff you put in your car engine. In chemistry, oil stands for oxidation is loss. Loss of what, you ask? Loss of electrons, of course. So whenever a substance, be it an atom, an ion, or a molecule, undergoes the process of oxidation, it's essentially giving away some of its electrons to another substance that's ready to accept them. It's like that atom is doing a bit of spring cleaning in its electron closet and generously donating some items it no longer needs as much. This donation process is absolutely crucial because those electrons don't just vanish into thin air, they always go somewhere else, which we'll talk about very soon. Let's consider a real-world example to make this clearer. Imagine you have a shiny, metallic piece of pure sodium. Sodium atoms, in their natural metallic state, have one electron in their outermost shell that they are not very strongly attached to. It's relatively easy for them to give it up. If this sodium metal participates in a chemical reaction, it often really likes to give away that one loosely held electron. When a sodium atom does this, when it loses that electron, it transforms into a sodium ion which has a positive electrical charge. This positive charge arises because it now has more positive protons in its nucleus than negative electrons orbiting around it. So, in this process, the sodium atom has been oxidized. It lost an electron, plain and simple. That's oil in action. You might be sitting there wondering, why would an atom or molecule to lose its electrons in the first place? That seems a bit counterintuitive, doesn't it? Well, atoms and molecules are often striving to reach a more stable, lower energy state. For many atoms, this stability is associated with having a completely full outer shell of electrons like the noble gases have. Sometimes losing an electron, or perhaps two, allows an atom to achieve that much-desired stable electron configuration. So, oxidation isn't always a bad thing for the atom or molecule involved. It can actually be a way for it to become more settled and less reactive, chemically speaking. It's a bit like finding the most comfortable and energetically favorable arrangement for itself within the grand, dynamic scheme of chemical interactions. Now that we've successfully tackled the concept of oxidation, let's turn our attention to its inseparable partner, the process called reduction. If oxidation is all about losing those tiny energetic electrons, can you take a good guess what reduction might be all about? You probably got it. Reduction is precisely the opposite. It's all about gaining electrons. It's the other essential side of the coin in our fascinating electron exchange game that we call a redox reaction. One substance in the reaction loses electrons, it gets oxidized, and another substance must be there to gain those very same electrons, it gets reduced. That's the fundamental and unbreakable balance that governs these types of chemical transformations. It's a perfectly matched pair of processes you see working in tandem. Just like we have our handy mnemonic oil to help us remember what oxidation is, we have another cool and equally useful mnemonic for reduction. Are you ready for it? It's RIG! And RIG stands for reduction is gain. Gain of what, you might ask? Gain of electrons, of course, it's as simple as that. So when a particular substance is reduced during a chemical reaction, it's happily and eagerly accepting electrons that another substance has generously given away during its own oxidation process. It's like that substance is attending a chemical giveaway event and eagerly picks up some free electron goodies that are on offer. This acceptance of new electrons significantly changes the chemical nature and properties of the substance that gains them. Let's think about another common element, chlorine, to illustrate this. Chlorine atoms, in their elemental form, are really keen to gain just one more electron. Gaining that one extra electron allows them to complete their outer electron shell, which makes them much more stable, similar to the noble gas argon. So, if a chlorine atom happens to encounter an electron that's up for grabs, perhaps an electron that was just lost by an oxidized sodium atom, for instance, it will almost certainly snatch it up very quickly. When the chlorine atom successfully gains that electron, it transforms into a chloride ion, which has a negative electrical charge. So in this scenario, the chlorine atom has been reduced. It gained an electron. That's RIG in action, as clear as day. So the term reduction might initially sound a little bit confusing, as if something is getting smaller or perhaps less important. However, in the language of chemistry, when we say a substance is reduced, it specifically means that its overall negative charge is becoming more negative, or, if it was positive, it's becoming less positive. This change in charge happens precisely because it's gaining those negatively charged particles we call electrons. It's a bit of a tricky word choice perhaps, but if you always remember the simple phrase RIG, reduction is gain, you'll always know that reduction means an increase in the number of electrons for that particular atom, ion, or molecule involved in the reaction. It's a very important concept to grasp fully. Here's a super important, absolutely critical idea that you need to remember about these reactions. Oxidation and reduction always happen together. They are like perfectly synchronized dance partners in a chemical ballet. You simply cannot have one of these processes occurring without the other one also taking place simultaneously. If one substance in a reaction loses electrons, that's oxidation, remember oil, then another substance must be present right there and then to gain those exact same electrons. That's reduction, remember RIG? Electrons don't just float off into empty space on their own accord for very long. They need to find a new atomic or molecular home almost immediately. This inseparable partnership is precisely what makes a redox reaction complete and balanced. It's a beautiful demonstration of chemical symmetry. Think of it like a simple trade or an exchange. If you decide to give away one of your toys, that's like oxidation, you lose the toy, the electron, then someone else must be there to take that toy from you. That's like reduction. They gain the toy, the electron. The toy in this chemical analogy is, of course, an electron. So, in any given redox reaction, what's really happening at the most fundamental level is that electrons are being transferred from the substance that is being oxidized. This substance is often called the reducing agent or electron donor, to the substance that is being reduced. This substance is often called the oxidizing agent or electron acceptor. This crucial transfer of electrons is the very heart of the reaction, driving all the chemical changes that we observe. This inseparable partnership is precisely why we call them redox reactions in the first place. The red part of the name actually comes from the word reduction, and the ox part of the name comes from the word oxidation. When you put those two parts together, you get the combined term redox. It's a clever little shorthand name that constantly serves as a reminder that these two fundamental processes are inextricably linked, like best friends who always show up to parties together. One process absolutely cannot occur in isolation from the other. If you manage to spot an oxidation happening in a chemical system, you can be absolutely certain that a reduction is also taking place somewhere in that same system, even if it's not immediately obvious at first glance. So, let's revisit our earlier example. When shiny sodium metal reacts vigorously with greenish-yellow chlorine gas, we know the sodium atoms get oxidized. They lose their outermost electrons. But where do those electrons go? They don't just disappear, they go directly to the chlorine atoms. The chlorine atoms, in turn, get reduced. They eagerly gain those electrons offered by the sodium. As a result of this electron transfer, the neutral sodium atoms become positively charged sodium ions, and the neutral chlorine atoms become negatively charged chloride ions. These newly formed oppositely charged ions then stick together due to their electrical attraction, forming the compound sodium chloride, which you know as common table salt. It's a classic and beautiful example of a redox reaction where electron transfer leads directly to the formation of a brand new chemical compound. Isn't chemistry neat? Let's take a look at a very common everyday example of a redox reaction that you've almost certainly seen with your own eyes: rust. When a piece of iron, like an old bicycle left out in the rain, a garden tool, or even a simple nail, is exposed to damp air for a period of time, it often develops a reddish-brown, flaky coating. That coating is what we call rust. The process of rusting is actually a relatively slow but steady redox reaction. It serves as a perfect and very visible illustration of how these fundamental electron transfers can dramatically change the properties of materials all around us. It happens gradually over time, but it's undeniably a powerful chemical process at work, transforming strong metal into a crumbly powder. So, what exactly is happening with those tiny electrons during the rusting process? Well, the iron, Fe atoms that make up the solid metal are the ones getting oxidized. That means the iron is losing electrons. Remember our handy mnemonic oil. Oxidation is loss. The individual iron atoms within the metallic structure are giving up some of their electrons, and in doing so, they are transforming from neutral iron metal Fe into positively charged iron ions, like Fe2+ or Fe3+. This change in the iron atoms from their neutral state to an ionic state weakens the overall metallic structure and is the very first crucial step towards the formation of that familiar, flaky, reddish-brown rust that we all know and often try to prevent. It's a chemical transformation happening at the atomic level. Now, if the iron is losing electrons, who is taking those electrons? There must be an electron acceptor. In the case of rusting, the oxygen, O2, from the surrounding air is the primary electron grabber. The oxygen molecules are getting reduced. Remember our other helpful mnemonic rig: reduction is gain. Oxygen atoms, which are quite electronegative, meaning they love electrons, eagerly accept the electrons that have been lost by the iron atoms. This reduction of oxygen, a process that is often significantly helped along by the presence of water or moisture, allows the oxygen to combine chemically with the newly formed, positively charged iron ions. This vital combination is what ultimately forms iron oxide, which is the proper chemical name for the substance we commonly call rust. For example, Fe2O3.NH2O. So, the process of rusting is a classic example of a redox partnership in action. The iron metal is oxidized. It loses its electrons and its oxidation state increases, and the oxygen from the air is reduced. It gains those electrons and its oxidation state decreases. This continuous electrochemical process slowly but surely eats away at the integrity of the iron or steel object. This is precisely why we often try to protect iron and steel structures with coatings like paint, galvanization, which is coating with zinc, or other protective layers. These barriers are designed to prevent oxygen and water from reaching the iron surface and initiating this electron dance that leads to corrosion. Understanding this redox chemistry helps us preserve valuable metal structures from degrading over time. It's very practical chemistry. Redox reactions aren't just about things breaking down or corroding, like in the case of rusting. They are also incredibly important for building things up, and one of the most vital and amazing building processes on our entire planet Earth is photosynthesis. This is the incredible chemical process that green plants, algae, and even some types of bacteria use to make their own food, essentially sugars, using energy from sunlight. It's the absolute foundation of most food chains on our planet, providing the energy that sustains almost all life. And guess what? The engine driving this entire magnificent process is powered by a series of complex redox reactions. It's truly a life-sustaining chemical marvel, perfected by nature over billions of years. In the process of photosynthesis, plants take in two very simple ingredients from their environment: carbon dioxide from the air, which they absorb through tiny pores in their leaves, and water from the soil, which they draw up through their roots. Using the radiant energy captured from sunlight, they chemically convert these simple inorganic molecules into a much more complex sugar molecule called glucose, which stores chemical energy, and they also release oxygen as a byproduct. Now, where's the redox in all of this? Well, the carbon atoms within the carbon dioxide molecules get reduced. They effectively gain electrons and also hydrogen atoms, which often travel along with electrons in many biological redox reactions to become part of the energy-rich sugar molecule. This is a huge energy storage step for the plant. So if the carbon dioxide is being reduced by gaining electrons or hydrogen, then something else in the reaction must be getting oxidized by losing electrons, right? Absolutely, you're thinking like a chemist now. In the grand scheme of photosynthesis, water molecules are the ones that get oxidized. The oxygen atoms within the water molecules lose electrons, and they also lose their hydrogen atoms in the process. These oxygen atoms, now stripped of some electrons and their hydrogen partners, combine to form oxygen gas, which is then released into the atmosphere. So, the very oxygen we breathe and depend on for our survival is actually a byproduct of water being oxidized during the light-dependent reactions of photosynthesis. It's an incredible life-giving exchange. Photosynthesis stands as a truly beautiful and elegant example of how redox reactions drive the fundamental processes of life on Earth. Sunlight provides the necessary initial energy to kickstart the process, but it's the intricate series of electron transfers, the redox steps, that actually rearrange the atoms from simple carbon dioxide and water into energy-rich sugar molecules and the life-giving oxygen gas we need. It's a highly complex and finely tuned sequence of many individual redox steps, but the overall magnificent result is that plants are able to capture solar energy and store it efficiently in chemical bonds, all thanks to this intricate dance of electrons. Nature is truly an amazing and ingenious chemist, isn't it? It's awe-inspiring. Ever stop to wonder how a tiny battery, seemingly so simple, manages to power your television remote control, your trusty flashlight in a power outage, or even your sophisticated smartphone that connects you to the world? The incredible magic that happens inside every battery is all about carefully controlled and cleverly engineered redox reactions. Batteries are truly ingenious chemical devices that harness the energy released when electrons move from one substance to another. They don't just let electrons transfer directly and chaotically. Oh no, that would just generate heat. Instead, they make those electrons take a specific detour. And that controlled detour through an external circuit is precisely what powers our beloved gadgets. Inside a typical battery, you'll find two different materials called electrodes. One electrode is keen to lose electrons. This gets oxidized at the anode, and the other is keen to gain electrons. This gets reduced at the cathode. These electrode materials are separated by a special substance called an electrolyte. The electrolyte is crucial because it allows ions to move between electrodes, completing the internal circuit, but forces electrons to travel through an external circuit, like the wires in your flashlight or phone. This forced pathway for electrons is the key to a battery's function. When you connect a battery to a device, you're completing that external electrical circuit. Electrons then flow spontaneously from the anode, the negative terminal, through your device's components. As electrons flow, they do useful work like lighting up a bulb, making a motor spin, or powering a microchip. After passing through the device, electrons travel to the cathode, the positive terminal. The oxidation at the anode provides electrons, and the reduction at the cathode accepts them. This directed flow of electrons is what we call electric current. Different types of batteries, like alkaline, lithium-ion, or lead-acid batteries, use different chemical substances, but the fundamental principle remains the same: separated redox reactions forcing electrons through external circuits. Eventually, when the anode can't give up more electrons, or the cathode can't accept more, the battery dies. For rechargeable batteries, we can force electrons back in the opposite direction, reversing the redox reactions and restoring the battery's potential. It's chemistry working for us in a very practical way. So we've firmly established that oxidation is all about the loss of electrons, oil, and reduction is all about the gain of electrons, Rig. But how can we actually look at a chemical equation, which is like a recipe for a chemical reaction, and figure out precisely which substance is losing electrons and which one is gaining them? It's like being a chemical detective, searching for clues. One of the main tools that chemists use to track electron movements in redox reactions is something called oxidation states, or more commonly, oxidation numbers. These oxidation numbers are like imaginary charges that we assign to atoms when they are part of a molecule or an ion. We assign them by following a set of rules, generally assuming that the electrons in a bond are completely held by the more electron-loving or electronegative atom. There are some relatively simple and straightforward rules for assigning these oxidation numbers, and chemists use them consistently. For example, an atom, when it exists in its pure elemental form, like a piece of iron metal or a molecule of oxygen gas or chlorine gas, always has an oxidation number of 0. For a simple ion that consists of only one atom, like a sodium ion or a chloride ion, its oxidation number is simply equal to its electrical charge. In most chemical compounds, oxygen is typically assigned an oxidation number of -2, and hydrogen is usually assigned an oxidation number of +1, except in metal hydrides. We use these and a few other rules to systematically figure out the oxidation number of each and every atom, both before a reaction starts, in the reactants, and after the reaction is finished, in the products. It's a bookkeeping system. Once we have successfully assigned the oxidation numbers to all the atoms involved in the reaction, both on the reactant side and the product side of the chemical equation, we can then look for changes in these numbers to spot the redox processes. If an atom's oxidation number increases during the course of a chemical reaction, for example, going from 0 to +2 or from +1 to +3, it means that atom has become more positive or less negative. This increase in positive character happens because it has lost some of its negatively charged electrons. Therefore, an increase in oxidation number is a clear signal that oxidation has occurred. For instance, if solid iron with an oxidation state of 0 reacts to form an iron 3 ion with an oxidation state of +3, as it does in some rust compounds, it has definitely been oxidized. Conversely, if an atom's oxidation number decreases during a reaction, for example going from 0 to -2 or from +1 to -1, it means that the atom has become more negative or less positive. This decrease in oxidation number or increase in negative character happens because it has gained some negatively charged electrons. So, a decrease in oxidation number is the telltale sign that reduction has taken place. For example, if oxygen gas with an oxidation state of 0 reacts to form oxide ions in a compound like iron oxide, where oxygen has an oxidation state of -2, or in water, where oxygen is also -2, it has clearly been reduced. By carefully tracking these characteristic changes in oxidation numbers, we can confidently and accurately identify exactly what's being oxidized and what's being reduced in any given redox reaction. Pretty neat, huh? It's a powerful analytical tool. Wow, science adventurers, we've certainly been on quite an amazing electron-fueled journey together today. We've explored the fascinating world of redox reactions and discovered that this incredible dance of electron loss, oxidation, and electron gain reduction is not just some dusty, abstract topic confined to the pages of a chemistry textbook. Far from it. These reactions are vibrantly alive and happening all around us, all the time, in countless incredibly important and often life-sustaining ways. From the slow, silent decay of a rusting piece of metal left outdoors, to the vibrant, life-giving energy creation that occurs within the green leaves of plants during photosynthesis, redox chemistry is truly at the very heart of it all. It's a fundamental concept that unlocks so much understanding about our physical and biological world. Just take a moment to think about it. The very energy that powers our bodies, allowing us to walk, talk, think, and play, comes directly from a series of complex redox reactions as our cells break down the food we eat through processes like cellular respiration. The electricity that lights up our homes, charges our phones, and powers our countless devices often originates from redox reactions, whether they are occurring inside a battery or in a power plant that is burning fossil fuels. Combustion is a very rapid and energetic redox reaction. Even seemingly simple everyday occurrences like using bleach to remove stubborn stains from clothes or watching a freshly cut apple gradually turn brown when exposed to air involve these critical electron transfers. Redox is truly a cornerstone of both chemistry and biology. Understanding the core principles of oxidation and reduction, perhaps with the help of handy mnemonics like oil, oxidation is loss and reduction is gain, and learning how to spot these crucial changes by carefully examining oxidation numbers gives you an incredibly powerful lens through which to view and interpret the chemical world around you. It helps you to see the underlying connections between processes that might, at first glance, appear to be completely different or unrelated. It's almost like having a secret decoder ring that unlocks the mysteries for a huge and significant part of all chemistry. This knowledge empowers you to comprehend how things work at a fundamental molecular level, which is, in my opinion, incredibly cool and deeply satisfying. So the very next time you see a battery powering a toy, notice a rusty gate hinge, admire a green plant soaking up the sun, or even just take a deep, refreshing breath of fresh air, a gift from countless photosynthetic organisms performing redox reactions. I hope you'll take a moment to remember the incredible, invisible, yet profoundly impactful dance of electrons. Redox reactions are absolutely fundamental to our world. They are endlessly fascinating to study, and they are truly, unequivocally, everywhere. Keep exploring the wonders of science, keep asking those important questions, and keep appreciating the amazing chemistry that makes our world go round and makes life itself possible. Science is all about understanding these incredible connections.